So welcome to our first unit that we're going to take a look at since we finished up the first exam. We're going to bring in this last part, which is really still from Module 3. So this is 3.7, and we're going to talk about something called the difference quotient. Difference means to subtract. Quotient means to divide, or a fraction. So we're going to be looking at a fraction that has a difference in it, a subtraction. And what we use subtraction for, or one of the primary uses of subtraction, is to calculate the distance between two items. Okay, so I'm going to start with something a little different than what we've been doing. I'll take a brief look over the PowerPoint, but then I'm going to switch over into looking at the lesson for 3.7 and actually working through some of the examples in there. PowerPoint has some examples, but we'll see how this all works. So we're starting off, we've got some kind of a function here, 1/2 t squared plus 3. If you remember from your earlier algebra, that would be a quadratic function. So it's going to have a graph that's curved, sort of U-shape, and it'll be up. So that's our function we're going to deal with, and we're going to look at what happens when we go from 4 seconds to 9 seconds. So this is a time is how it's moving, right? And then this function is giving the distance in feet of the car from the crosswalk, so as it moves away. And we will be able to basically calculate speed, right? So distance and time, if we have both our time and our distance, we can get at something. If you take distance divided by time, you get the rate, the speed. Okay, so we could calculate this going from 4 to 9 seconds. If you plug in 4 for t, you would get the distance is 11 feet from the crosswalk, and if then you plug in 9 for t in this formula up here, you end up with the answer of 43.5. If you subtract those, 43.5 minus 11, then you get the total change of 32 feet, 32.5 feet. And so we're going to take a look at a graph. So this is, again, the parabola is going up, and we're looking at what happened at 4 seconds, and we got the value at 9 seconds. So this gives us a point 4, 11. And this gives us the 0.9. Again, plugging in 9, I think they had 43 point something. Let me, so I tend to forget these things, but let's go back. 43.5. Okay, I know it's. And you see what we're basically getting is we calculated the change in distance as being subtracting these two things, 32.5, and then subtracting the change in time, 4 to 9, 9 minus 4 is going to give us 5. And when we do this, what we're going to get is the average rate of change. Okay. And we see that it's not a constant speed, but it's giving us an average speed, average rate. Okay, so a few other questions to answer, but I think that's going to be enough. When we look at this, we've got the point 4, f of 4, which again, when you plug in 4 to the formula, we calculate that as 11. 9, f of 9, well, what is f of 9? Well, that's what happens when you plug 9 into the function. And as we saw earlier, that gave us 43.5. So part of it is getting comfortable with this notation. we're going to have, what we did is we took the y value when we plug in 9, we subtracted the y value when we plugged in 4, and then we took the x value of 9 minus the x value of 4, and that's what we're going to call the difference quotient, right? This is going to give us an average rate of change. And what we do to get f of 9 is we plug it in, and we saw that was 43.5. f of 4, when we plug that in, we got 11. And then 9 minus 4, we could go ahead and do that and get 5. 43.5 minus 11, we calculated as 32.5 over 5. And then you could make this into a decimal or just leave it as it is as a fraction, but this is in units of feet per second, right? Feet on the top, seconds in the denominator, which is a rate. It's a speed, 32.5 feet per 5 seconds. Okay, average rate of change. So that's what we're going to be doing. We're going to be looking at this as the difference quotient, but we're going to add another variable into here as we do it. And so at this time, I want to switch over to the lesson. So let's take a look here. And again, you'll be able to also pull up the lesson, and let's make it a little bit bigger. So this gets another example, but what I want to focus on sort of is the technique of what we're getting is the slope, the average rate of change between 2 points. We've got the y values on top, so this is really, remember if we think about it in algebra, it was y2 minus y1 over x2 minus x1. We're doing exactly the same thing with some new notation. So we're listing y2 instead of as y2, we're listing it as some function with the x value plugged in minus the function with the y value, or sorry, the other x value plugged in. So in the numerator, we have 2 y values. In the denominator, we have 2 x values. Okay, so we could think of these as the point 7, h of 7, and the other point would be 2, h of 2. Okay, so that's how we would recognize it in general. Again, the bottom is going to be a difference of 5, and so we would, now they don't actually give us the function. They do give us how many yards they went during that time period. But again, we can write this as h of 7 minus h of 2 all over 5. Now this doesn't look like a slope anymore because we have combined the denominator. We haven't done the numerator yet because we don't have the formula to plug it in, function, and get the y values, but we'll look at some examples where we do. Okay, so we're going to walk through this one, and we're going to actually do it with particular values. We'll follow through on that, and in working through this together, we'll get a good feel, and then we'll go to some of the more abstract uses of the difference quotient, which why we're doing this is this is something that will prepare you for calculus. In your first 2 weeks of calculus, you will be using the difference formula, the difference quotient, to find an average rate of change for functions that are not linear. Okay, so first let's walk through here. This time we do have the function, And we're told that it's the altitude of a plane, so the output would be how many thousands of feet above the earth that the plane is, or above sea level, in terms of the number of minutes since lifting off the ground. Okay. Hopefully you can see that, when at time 0, before it lifted off, it was already actually 2,000 feet off the ground. So that tells us the airport was 2,000 feet above sea level. Let me put, not 2,000, above the ground, above sea level. So, okay, what was the plane's altitude 1 minute after lifting off? So 1 minute means x equals 1. So what they're asking us to find is, what is f of 1? And we're going to do that by plugging in 1 for each of the x values. Like 1 squared is 1. 1 times 5 is 5, plus 2, so that's going to give us 7, 8. So f of 1 equals 8. So they're, after 1 minute, they're already up to 8,000 feet above sea level. What's the distance or altitude after 4 minutes? We do the same thing we did with 1, except now we plug in 4. Okay. And you could use your graphing calculator, look it up on the table if you want, but I'm just going to go ahead and go through the mathematics, since our function is fairly straightforward and the numbers we end up with are fairly easy to work with. 4 squared is 16, 5 times 4 is 20, plus 2, so you got 20 and 16, that's 36, plus 2 is going to give us 38. So what we have is f of 4 equals 38. So we could fill that in. Now evaluate the change in the altitude from 1 minute to 4 minutes. So the change, we're going from 38 to 39, or sorry, 38, well, we're going from 8 to 38. But all they want is that change, so that's 38,000 feet minus 8 feet, gives us that the plane changed by 30,000 feet. And notice they have the units here. Use function notation to represent this change, computed in part C. Well, what did we do? We did f of 4 minus f of 1. And then use function notation to represent the average rate of change. So we've got just the change, right? This is just the amount of change. To get the average, we've got to figure out how much did it change over this time period from 1 to 4 seconds. And so we do the same thing, use function notation to represent it. Now they don't want us to actually calculate it. Let me move it up a little bit so we can see a little bit more. But they want us to think of this as f of 4 minus f of 1. Now you could actually do the calculation of 4 minus 1 is 3. I think it would take that, but you could also put it in as 4 minus 1. We've got the full difference quotient here. And we can see that this is really a slope. 2 y values in the top being subtracted, the x values in the bottom. Now it wants us to actually determine that average rate of change. So we would continue to do the calculations, right? We plug in the numbers, 38 minus 8. We got those, f of 4 is 38, f of 1 is 8, over 4 minus 1. So that's going to give us 30 divided by 3, which is going to give us 10. And that would be, the selection will be 1,000 feet per minute. Thousands of feet, or 1,000 feet per 1 minute. Okay, so we could put that in. So what is it? The constant rate of change that would result in the same altitude change as a plane on the 3-minute interval from x to 1 since lifting off. So if we looked at it as a constant rate of change, this is what would be needed. we know from the function it's quadratic. It's not a straight line. It's not really the actual rate of change of the plane, because what we're getting is an average. So it's a constant rate of change that would need it to make it happen. So that's what we're thinking of. We don't actually have an actual rate of change. We don't have the actual path. That's the function with the x squared. Okay, so what we've done is, again, like we talked, we're getting the slope of a straight line that would connect those 2 points. We use the function values to get the y values given the x values, right? So this y2 is really f of x2. That's how we got it. And this y1 is f of x1, just a different way, different symbols to use. So we do the subtraction. We've got the average rate of change. We also call this a secant line, so you'll hear that used. It's not a big deal whether you remember it or not, but just it is a secant line. And if this line were the way it was traveling, that's what the rate of change would be between the 2 points. But for us, it's an average, and we see that actually as a plane takes off, it actually speeds up. That's why it causes it to curve upward. Okay, so now we're going to use this. You could kind of work through this, but we've kind of, I'll do this sort of more quickly. So this is an x value and a y value, an x value and a y value. And the reason we're going with x plus h, notice we're at x, we're at some value x on the x-axis. They don't tell us what it is. This x plus h is, we add some distance to this. And again, it's an abstract, it's a variable amount of distance. But these are going to be our 2 x points, and then they would give us the 2 y values from the second part. Okay, and the reason we're doing this, because when you get into calculus, what you're going to do is, now we've got this variable h, we can let h get smaller and smaller and actually go all the way to 0. And what that's going to allow us to do in calculus, not in this class, but in calculus, it will actually allow us to get the rate of change at a point, instantaneous rate of change. So we're setting you up for next semester, when most of you will probably be taking the calculus course. So what the amount of change is the 2 y values subtracted. So we'll go with y2, which is f of x plus h. And then we subtract the other y value, which is just f of x. And then, so that's this first part. And this is using function notation. That's kind of what I've done. And then represent the average rate of change. So I'm kind of jumping all the way down to here. The average rate of change is going to be x plus h, right? The x coordinate from the second point minus x. And what we see is x minus x is going to cancel out. So when we simplify it, f of x plus h minus f of x, it no longer looks like a slope formula, because you don't have the x in the denominator anymore. You just have this distance h, which again, we're at some distant point next semester, we're going to get another technique that allows us, it's called the limit, to let h actually go to 0, and then we'll get the rate of change at a point. Today, in this class, we're working on the concepts and the skills needed to do that. Okay, so this is what we call the difference formula, and you can see the first part here looks like a slope, right? Y minus y, x minus x. But the way we end up using it, what we really call the difference quotient, has been simplified so it doesn't look so much like a slope anymore. But it is, because it's just been simplified. And what we're going to see is that as we take some of these examples, a lot of things in the numerator will also cancel out. So we'll kind of walk through this, and then we'll do it on our own. So what is f of x plus h if this is our function? Notice there's two places to plug in the input here. And so just kind of when you start to do this, I'm going to write sort of what I do as the first step. Is you take the function f, which is x squared minus 4x, you rewrite it with open parentheses, so that's x squared minus 4x, and then inside those parentheses you put the x plus h. Now, if you don't do that, the difficulty you're probably facing without realizing it is it's really, your mind is saying you can't just take x plus h and put it in for x because there's an x and that's an x. Aren't they the same thing? What I'd like to say at this point is some wisdom from one of my students from Oregon State who said that, well, no, x is just, it's like on a treasure map, it marks a spot. So in the formula up here, x is just marking the place where we're going to put something. In this case, we're being told to put x plus h. In this case, we're being told to just put the x back in. So that's why you get sort of these two parts, f of x, and this really expanded form of f of x plus h. Okay. Now let's just walk through the steps a little bit. You've got x plus h squared. You've actually got to FOIL this out. It's not just going to be x squared plus h squared. It's x plus h times x plus h. And then using FOIL, I'll just close that off. X times x is x squared. X times h is xh. And then you've got h times x, which we also write as xh because the order's multiplication's commutative. And then we've got the last terms, h times h plus h squared. And notice that we do have two like terms, xh and xh. You can add those together and get 2xh. So x squared plus 2xh plus h squared. And that's what they've done here. They've just done all that work, but they didn't show how they got there. So that's, and typically what I found is this is where students will struggle. This is the hard part, right? The hardest part. The other part is that this negative right here has to just go with the 4, and it distributes to both. So that plus h now becomes minus 4h. Oh, wait. Yes, okay, so that goes there. So you get your minus 4x minus 4h. So that's all of this ends up being plugging in x plus h to the function. So that's how we got that. Second part, you just plug in x, so really you just take a copy of it, x squared minus 4, that goes there. They left this x plus h minus x in the denominator, which is kind of nice because that helps it look like a slope. When they got to this step, you might have missed out. What they had to do is they had to distribute this negative to each of these. So then you've got a minus x squared plus 4x. And notice in the first part, f of x plus 8, you've got a minus 4x here and a plus 4x, so those two are going to cancel. You've got a minus x squared and a plus x squared, so those cancel. This kind of always happens. The back part is always going to cancel out things in the front, and all that's left are the stuff with the h, so you get 2xh plus h squared minus 4h. And we'll work through this together. I just want to give you an overview. And then what you can do is you divide each of these by h, right? You distribute the division to each of these. So you divide out an h, and you're left with 2x. H squared now becomes just h, and the 4h and the h in the bottom cancel, so you get minus 4. So that's what we're doing. This is what we're going to be shooting for. And then in calculus, you'll see now we're actually able to let the h become 0, and so this gives us something called the derivative, the slope at a point, instantaneous rate of change. So we've gone from average rate of change to instantaneous rate of change. That's why we're doing this. So I'm going to look at these next two examples. This one's very similar, but I think if we walk through it without all the already done stuff, you'll see how to do it. And then in the homework, there's one similar to this, and it's a little more challenging. So we'll look at those two, and then we'll call this lesson ready to be implemented. Okay, so we're given this function, x squared plus 9, and we're being asked to express in terms of x and h that represent the average rate of change of f over the interval of length h. So remember, h is, we're starting at x, we're going some distance h, something made up variable. Your h could be smaller or larger than my h, but it allows us to change it. And so what they really want is the average rate of change. Remember, that's really just slope. Okay, so I think I've got enough room to work on it here. What we want, starting with the difference quotient, is f of x plus h minus f of x. And again, you could just put h in the denominator, but I'm going to go ahead and put x plus h for the x coordinate of the first point minus x for the x coordinate of the second point that we're working with, maybe the first point, however you want to look at it, right? So this is going to simplify, but what I see is I've got to get f of x plus h. So what I need is I come back to the function that was given. We're going to write the two things, and I'm going to do it this way vertically, and I'll show you. I think it's going to make things easier for us as we work through this. So what is f of x plus h? Well, the function is x squared, so I write that as big parentheses squared. So that's x squared, right? I just have changed my x into a big open parentheses, which is a perfect symbol for an input because it's got a lot of space to put something, plus 9 times the input. And now let's go ahead and change colors. What goes in here? The input, x plus h and x plus h. We're going to simplify this. And again, this one can be a little difficult in that you have to take x plus h times x plus h. But you'll see that once you get used to it, you'll get it down. But let me do it over here. It's x plus h times x plus h. Repetition's the key. So once you work through things several times, as long as you're looking at it for understanding, it typically leads to greater understanding. So that was the first. Now we're doing the outer. So that's xh. We're going to do the inner, h times x, which we also write as xh. And then the last, h times h, gives us h squared. We simplify it down to, by adding like terms, x plus h is 2xh plus h squared. Okay, so that's the first part up here. We'll go ahead and put that in. And then we distribute positive 9 over here. So we're going to get a plus 9x plus 9h. No like terms left. But what I'm going to do next, let's change back to red, is I'm going to put right below here f of x. So instead of copying all this stuff over to this formula, watch, I'm actually going to do my subtraction vertically over here. So what is f of x? It is just x squared plus 9. In this case, I'm not going to be plugging anything in for x, so I just leave the x there. So I'm going to put that here. I'll put x squared here plus 9x. I'm going to put that there. Okay, now part of the thing is this f of x plus h, which is this statement here, this expression, minus f of x. So I'm subtracting the bottom part, right? So that means when you subtract, you change the sign. That the negative sign has to distribute through to my f of x, right? I want to subtract f of x, which means each of these signs will change. Okay, so I get rid of that plus. What's a cool thing is now that I've written it this way, I don't know, it's cool for me anyway, is that you've got your stuff that's going to cancel lined up. X squared minus x squared, well, that's 0, right? So what is left? 2xh plus h squared. That didn't get canceled. Plus, okay, I got that. Plus 9x and minus 9x, those cancel. That's 0. And so then there's a plus 9h. That's all that's left. And so instead of rewriting this up long form, I've done it vertically, which allows easier subtraction. So this is now my complete numerator. And what I just need to do now is put it over the denominator. And I'm going to, while I do that, positive x minus x, that becomes 0. All that's going to be left is this h. So that's all over h. Now I'm not quite done because each of the terms in the numerator has an h. So what I'm able to do is to distribute the division of the h from the bottom into each of these. So I divide each of those by h. And that's going to give us our final answer of 2x, right? H divided by h is 1. H squared divided by h is going to be h. And then 9h becomes, not h divided by h is 1, just becomes 9. So we use the difference quotient to come up with a formula for the average rate of change. Now you can change whatever h is going to be, and you can get the actual, change the value of x actually. You'll get a formula. You'll see eventually you'll let h become 0, which gives us the sort of a function that would give us the instantaneous rate of change. Okay, I'll let you try the next one. Is going to be similar, except it's got this 3. Maybe we should have done that one because it's harder, a little bit harder, because then the 3 distributes through. But you'll see if you follow the same sort of pattern. Find f of x, or sorry, f of x plus h. Write it out longhand like this. Underneath it, put f of x and then put minus f of x and change each of the signs. You'll see you always get all of whatever f of x is going to cancel because everything's got opposite signs. And so then what's left is what's going to be in the numerator, and then you just need to divide it by h. Okay, so that makes it nice and very doable with these type of questions. Let's take a look at one more example. It's a little more challenging. So what do we do with something that's like 4 over x? Okay, again, we're going to be doing the same thing, difference quotient. So we do f of x plus h minus f of x. And again, if you write this down repeated times, it becomes more second nature. You see this is y2 minus y1. And in the denominator, you get x plus h minus x, x2 minus x1. So our first step in doing this is to find what is f of x plus h. The first step is to take the function 4 over x and rewrite it, change the x to a big open parentheses, write exactly where it is, and then what goes in that parentheses? X plus h. Now the thing here, there's nothing more to do. There is nothing more to do because you can't expand this. You can't really do anything with it. So we're going to leave it, and we're going to see that the reason I'm doing this one has a slightly different approach. Then what is f of x Well, that's simply going to be plug in x for x, which is just 4 over x. Now again, we're going to subtract that. So kind of like what we're doing before, we're going to subtract, which makes that negative. But there's no way to vertically subtract these. We're going to have to take a look at a different approach because we've got two fractions. What we're going to need to do is get a common denominator. Okay, so this is kind of more challenging. So to do that, I'm going to come back to our difference formula, difference equation, difference quotient. I like to use all different names for it because I have a hard time thinking of the word quotient. Okay, so f of x plus h. So that's this part over here, 4 over x plus h. So let's write that. Minus f of x. So that's this part here. That's where that minus is, minus 4 over x. And this is where in the denominator we might go ahead and simplify. X minus x is 0, so all that we have is h. So when we have fractions that we're dealing with, one technique is to get a common denominator. So the first one, x plus h, is missing just the x, right? So we're going to multiply the denominator by x, but also the numerator. And that's like multiplying by 1, or it is multiplying by 1, so it doesn't change anything. The second part is missing the x plus h, so we will multiply by x plus h over x plus h, which is another way to write 1. So we're multiplying by 1. When we multiply by 1, nothing changes. Think about it. 5 times 1 is still 5. All right, it always works. Okay, so let's come over here. So then we get this x times 4, so that's going to be 4x. In the denominator, we get x times x plus h. We're going to see that this is probably going to cancel out somehow, or so we actually won't multiply it out. Let's leave it together. X times x plus h. And then we're going to subtract 4. Now up in this numerator, we are actually going to distribute. So 4x plus 4h. And sometimes it's just, I do these things because you find out after doing them a while, it's quicker to do them. If you're not sure, you can always multiply it out, and if you didn't need to, you can put it back together, or, it doesn't matter. And then the denominator is x times x plus h. And this is still all over h. I don't know if I'm going to have enough room here, so we might, what I'm going to do is I see above, I do have actually more room up here, so I'm going to use this upstairs. So I'm going to move upstairs, but what I want you to see is this has a common denominator, so I'm going to write that common denominator of x plus h. This is how we add fractions, right? We get them common denominator, or subtract fractions in this case. Get a common denominator, and then in the numerator we're going to get 4x. Now one of the things you want to see is that this negative is going to have to distribute to both of these terms. Minus 4x minus 4h. Okay, so that's how that worked out. All still divided by h, right? So we've got a complex fraction, a fraction on top of a fraction, or within a fraction. Okay, so now we can start simplifying. So 4x minus 4x is 0. Let's see. And what I'm going to do is, while I'm doing this, I'm going to simplify this fraction, but I'm going to divide by h. A way of thinking when you're dividing by h, right? That's like h over 1. Remember, when we divide fractions, we turn it to multiplication of the reciprocal. Oops, not 2, h, 1 over h. So watch this. I'm going to simplify this numerator, 4x minus 4x is 0. So we're left with negative 4h over x plus h. And then I'm going to multiply that by 1 over h. I would have divided it by h, or h over 1, so it turns the multiplication and becomes 1 over h. Just remember, when you divide by fractions, you always flip and multiply. Okay, so one of the things we can see right away is we have an h in the numerator, and this is all multiplication. That's an important thing, at least these, things being multiplied. So this h can divide into this h. And so now we are left with just negative 4 times 1. It's negative 4. And in the denominator, we could leave it that way, but actually I'm going to go ahead and distribute it. This is going to be x times x is x squared plus x times h. Maybe I could have done that earlier too, and it would have been okay, but and what we're going to see is that, again, this is where we stop. Let me get my eraser. I like things to look a little cleaner. So x, h. What we're going to see is that this is our final answer. So again, the steps are, when you've got a fraction, the steps we had to do is to get this common denominator. I imagine this will be the place that is the most difficult. Typically, working with fractions is one of the most mathematically difficult things, even for advanced mathematicians or people who've been doing it for 24 years and stuff. I still have problems with it because of flipping and everything. And then we get things to cancel out. We'll see when you get to calculus that you can actually, if you let h go to 0 now, that this is actually the derivative. And it's okay because we don't have division by 0. Now, if we try to put 0, h becomes 0 over here, we're dividing by 0, and that doesn't give us anything. So that's a whole trick that we're doing. I don't know if people don't say it's not a trick, it's something that always works. A trick sometimes works, doesn't work. I call them tricks. It's a skill. It's a skill. Let's put it that way. Okay. Learning how to use this average rate of change. H is just a technique of putting in an extra variable that we are later on going to make it, because we can make h be anything we want. We can even make h be 0, which we eventually do, and we're going to see that we're able to get the derivative, not the average rate of change, but the instantaneous rate of change. And notice we're starting with the average rate of change. With algebra, all we can do is get the average rate of change. But to get the instantaneous rate of change, we need calculus, and these are the skills that we're building up so that when we do get to calculus, we're able to take that leap of those first 2 weeks. We're going to do well in them, and we're going to make really good progress. Okay, so I think that's enough for this lesson, and I'll get on working on the next one. Thanks.